So today we are going to start our lecture from the book, and you can download the book from the Blackboard. I have already shared the Blackboard book on the Blackboard. So this might be yes. Is it visible to all of you? So we are just recapping the shared memory architecture. Unfortunately, due to a very busy schedule and some other works, I'm not been able to produce some smart or bullet-based PowerPoint for you. So, however, I will find something over here and then I will share it with you as well. So we are just recapping the chapter 4. We did earlier with that before the midterm exam. So this is about the shared memory architecture. So we are going to study that shared memory systems for measures categories of multiprocessors. In this category, all processors shares a global memory. So the linchpin which actually we need to study and we need to understand is the global memory. So there is only one memory. If it is a global memory, we know that there is a problem occur, which is like multiple processors are accessing a single shared memory, which creates a shared memory a problem, and that problem is known as cache coherency. So the author is also saying that interconnected network, you can see in the figure 4, two main problems need to be addressed while designing a shared memory. One is the performance degradation due to contention, like keeping contented elements more than once or creating a duplicacy can create a performance degradation, like you will create a heap of all those data which is actually available, so you are keeping contenting the elements repeatedly. And the second problem which what we are looking is towards is a cache coherence problem. So the performance degradation might happen when multiple processes are trying to access the shared memory simultaneously. In this way, what we are going to have, that's a typical design sort of an issue by which a cache resolves the contention problem. So again and again going to the memory, finding and keeping and bringing the same attribute to your own work in an environment when you are contented in a single chip. So that creates a problem for all of you. So however, you can see that they have a multiple copies of data spread throughout the caches. So you can say that every processor is actually keeping the same data into the memory. So you have multiple copies altogether, like if you have siblings, brothers and sister, and they are all to your same age, and they went to the shopping and they bought actually the same dresses for themselves, and they want to keep them in the cupboard, which is actually a shared cupboard, which is a global access. So it has a problem that you have multiple copies of same dresses available in a single cupboard. That's the one problem. The second problem is the coherence problem. The copies of the caches are coherent if they are all equal in the same value. However, if one of the processor writes over the value of one of the copies, then the copy becomes inconsistent. Like in this case, that if you have one content available in the memory and other processes are trying to access it, so they can change it if they are going to access it, like a shirt from the cabin. So what happens that if your elder brother is going to access it, wear it and went to some party, so it brings a problem for you that you want to access it and the content is actually not available. So we have earlier discussed such a kind of a problem with it. That's a typical example of the shared memory system by which you can design You can prepare a combined and a global memory interconnected with number of processors altogether. So beside it, we have some classification of the shared memory systems. The simplest shared memory system consists of one module, which is called to be as an M. So if it is a global module, so you can maybe write as M and a small g altogether. So we have number of processors, but right now what we are considering P1 and P2 processors. So according to our figure 4.2, the P1 and P2 must be connected with M in a shared manner, like both are accessing the M. Request arrive at the memory module through its two ports. An arbitration unit within the memory module passes request. Every time you have to pass a request to access the memory, you go to the arbitration module, which can pass a request to the memory controller. If the memory module is not busy, the single request arrives. Like if you want to access it, you can have those attributes connected and you can easily say it to them. So by this way, we know that the module is placed in the busy state while a requesting is being serviced. If you process a request, if you want to process something and you have already requested a memory module, so in this case you have to wait. So there are one more ways. I have earlier discussed it with you, that you can say it as a short wait, long wait. We have already discussed in the interrupts. So by this way, the memory module send a wait signal. So what you need to do, if it is busy servicing a previous request, then the memory module send a wait signal through the memory controller, the processor making the new request to it. In response, the requesting processor may request sometime later. Like sometime later means it is actually wants to have a reschedule process. So if an arbitration unit receives two requests at the same time, it can select one of them and passes it to the memory controller. Again, the denied request can be either held to be serviced next, or it may be repeated some later time. So next means service next means it is scheduling the processor to be serviced just next, like it is making a queue. So by the method of queue, you can introduce 1, 2, 3 processors to be served one by one. So if it is not queue based, if it is selection based, so they can select a time, like when this process will end, or these all those things have happened. We are least concerned that this process might end, but we will say that we will schedule, or we will make a schedule of the all the processes to be like the 8 p.m. So like if we say we are going to offer anything to a processor, like we want to process it. The processor has an arbitration unit which has a likely chance to decide two processes to be handled. So based upon the interconnection network use, shared memory can be categorized as the following. So we have earlier discussed the uniform memory access, which is called as a UMA, and that's a UMA in two parts. Then we have discussed the SMP architecture based upon the UMA, which is a shared memory system. Then that we have studied the NUMA, which is non-uniform memory access. In this case, every processor has their own memory. So over here, if we go back, that's a shared memory, but the module are actually different, but it's a packeted in a single chip. So every time when you are accessing memory, you must have to follow the same chip package. But however, we have distributed the different packages according to the processor in the NUMA architecture. So then we have another architecture, which is the least architecture with the memories over here are the COMA architectures. It is some likely simple and common like a NUMA architecture. And then the Kendall Square Research KSR machine is an example of such architecture. You can see in the figure 4.5 shows the organization of the coma. So we are going to look towards the figure 4.5. In this architecture, they have just added one more thing: the processor with again a caches, and then something which is added over here, and that is called the cache directory. So they differentiate with previous architecture. Even adding a single module, they have added the cache directory, which is different from the NUMA. So based upon the multiprocessor with a shared memory architecture, we have another topic to be discussed, which is a bus-based symmetric multiprocessing. So we have a bus which is actually connecting the shared memory systems all together. So in this case, the simple network of the shared memory system is the bus. So bus cache architecture elevates the need of expensive multi-ported memories. Multi-ported means like more than one processors are connected together on a same memory with the number of the ports available to access it. So however, the bus may get saturated if multiple processes are trying to access the shared memory. It is simple as that you have a garden in your house, so you can accommodate 50 people at a time. But if you have 100 people coming up, so you are not going to access this. So the passage or the garden which is available to accommodate only 50 people might not help you to accommodate the 100 people. That causes the situation to be saturated. It's so saturated that you cannot access other people as well. So in this way, what you need to do, if you have again the same method, that you distribute people in the type of the shift, that this shift should come after this, or you can ask the people to let the first shift to be ended, or first 50 has to be uh, cleaned up, so that you can allow the next 50 to be accommodated in this case. So a typical bus-based design uses cache to solve the bus intercontention problems. High-speed caches connected to each processor on one side. So every time when you talk about high-speed caches, so they have only one port which is connected to each processor, like in the picture above we have discussed, on one side, and the bus on the other side. So if we go towards the picture over here, you can see a bus is over here, and then you have a cache directory which is connected towards a single bus. So if you go to the interconnection bus over here, it is the same diagram as the coma, but however, in this chapter we define the variables for hit rate. We have already discussed the hit rate, the number of processors, processor speed, bus speed, and the processor duty cycle as well. So the effective bandwidth of the bus is bi fetches the second uh, per second, fetch per second. If each processor is running at a speed of v, then misses are being generated with the rate of v product with 1 minus h, and we can notate that h is actually the hit rate. So the total miss rate is actually the 1 minus hit rate. So we have calculated that the hit rate is 50%, so the hit rate is 0.5, so we can say the miss rate must be 0.5 as well. 1 minus 0.5 becomes the 0.5 for n processors. So we have discussed it earlier. There is an example as well. uh, Hopefully it is a similar example as given in the exam, but it's you have to, there is a solution as well, so you can solve it. So basic cache equivalency methods the cache memory coherence. In a single cache system, coherence between the memory and the cache is maintained using one of two policies. One is the write through and the second is the write back. We have discussed is as well. Then the cache coherence example. In the multiprocessing system, when a task is running on a processor P, requires the data in the global memory location X. For example, the content of X are copied. X are copied to processor P's local cache. So what happens where it is passed on P? Now suppose processor Q also access X. What happens if Q wants to write a new value over there? Like two processor X, like two processors are accessing the same X memory. So the memory name is X. Number one processor is P and the second processor is Q. So P and Q, P is already accessing it, however the Q wants to access it. In this case, the memory is going to have a cache coherence problem. So every time if P is going to change, you need to let the Q intimate it that we have actually changed the P. So that's a write through and write back problems that P reads after X. So write through it resolves, and write back it resolves the map and the cache. Then there is a sequence every time if P is X actually being changed. So P reads and P updates X so that the queue must know that the memory and the cache all are accessed. In a write back process, the memory is not being accessed. However, the thing is which is available in the cache is changed. So we can say that write back process is bit not such effective than a write through process as well. So write update versus write invalidate. So every time when some attribute is changed, so what happens? P reads X, then if P is changed, so P's cache is the local cache is changed, then Q read X, Q find something, Q update X. Before P writes something to Q writes something on X and change the element. Like previously the value of X is 5, so P knows 5, Q knows 5. The third step is Q says that the X, which is actually 5, is equals to 5 plus 1. So this time the value of X becomes 6 over here. I'm discussing this step. So by this method, the P caches is changed and the Q cache is changed. As we know that the write update is much more better than other approaches. So by this way, if Q updated the X, so the value becomes X double dash, and the in write invalidate, the P's cache says is an invalid value for X. So they might not accept the value updated by the Q. So the shared memory system has 4 combinations: write update, write through, write update and write back, write invalidate and write through, and write invalidate and write back. So we have already discussed the snooping protocols before the mid class, and we've been through the invalidate and throw methods earlier. We have so many things in this chapter we have discussed, and it came to mean right now that okay, this one has to be discussed with the slides and earlier before the midterm so that you can achieved and studied about it. So the protocol categorization, which is actually lies into a structure of a memory directory. So when you are deciding that we need to have some protocols categorization based upon the number of the blocks of data and based upon the number of the pointers to specify the location. As we all know, and I presume that you know about the pointers. Pointers are used to point the index location or the memory location inside the memory. So pointers might not come into the cache. So in the cache, we need some different sort of addressing technique we have discussed earlier before. So over here, the protocol categorization includes a full map directory. In the full map directory settings, each setting directory entry contains n pointers. So you have not limited your pointers to a specific unit. However, you can make it. But over here, we are taking typically n number, which is a very generic number in the number of the processors. So therefore, there could be n caches copies of a particular block shared to all processors. For every memory block, an n-bit vector is maintained. So when we select a block in a full map directory, we actually choose a vector to maintain, and that vector access the memory by the help of the pointers. So this is how the write update and write back protocol should work over here. In the next phase, we see that there is a limited directories as well. The limited directories have a fixed number of the pointers per directory. So we have actually limitize the number of the pointers, and based upon the number of pointers, we found that the steps are actually increased. If we say that previously steps, the problem was solved in the 4 processes over here, and over here the process is solved in double and twice as the time of the memory map problem. So that's a memory directory structure. In this directory structure, the memory is connected with the interconnection network, and they are actually connected with the caches, multiple number of caches, each cache containing the data accessed from the main memory. Similarly, the limited directory, they are doing the same thing, but the only difference actually over here and in here is the memory has the number of the blocks. However, over here the memory has the number of the pointers. So finally we will go towards the invalid protocol as well. So invalid protocol has multiple connections with it, like they are actually getting the C attribute and the data attribute all together. So that C attribute and C is actually the shows the caches. So in this way, like over here, if you can go through it, the cache C0 and cache C2. So they are actually used for the caches. However, the number of the letter X donates with the memory block. So we will go towards another topic, which is a scalable coherent network interface. So in the scalable coherent network, we define to connect the multiple memory architecture with the scalable coherent interfaces. So every time we have interface, we actually connect two things to like a processor and the memory on the same interface. So SCI is a protocol based on the doubly linked list or distributed directories. Each cache block is entered into the list of the processor sharing that block. So every time we maintain a list, and that list is actually liable to keep the record of the number of processors accessing a single memory. For every block address, the memory and the cache entries are additional tag bits. Part of the memory tag identifies the first processor in the sharing list. Like if you maintain a list of the number of processor P, Q, R, S, T, so the first processor which is actually the head of the queue. So part of each cache tag identifies the previous and the following sharing list entries, so that you can go to the next processor that is going to access the memory. If we go towards the centralized directory invalidation problem, so every time when you request something, if you are getting confused with the word invalidate means you put something in your pocket, like some bucks in your pocket, and then you want to access it and the bucks are not available in your pocket. So whenever you have the same situation, you put $5 in your pocket and then it retained $2, so you will say, okay, that's an invalid outcome. So that is a similar in the centralized directory invalidation problem. So they have again introduced something, Stanford Distributed Directory, which is called SDD. The Stanford Distributed Directory protocol is based on the singly linked list of distributed directories, similar to the SCI protocol. Memory points to the head of the sharing list. Each processor over here now points only its one predecessor. So the hierarchy knows that which is actually the last coming items. So every time I know the predecessor, it does means I know the node which is actually coming before me. So if I talk about predecessor, so you are actually your predecessor is your father and your successor is your son. So actually you are the successor of your father and your father is the predecessor of you. So over here, if we say like pretend in this diagram, if they are pretending that cache 0 head and cache C2 is invalid, so over here how we can find it, that the both CO, which is actually the head, is considered to be the middle and C2 is the head of the memory. So they have actually realigned the memory so that you can find the right uh, memory module to be selected and not to be called as invalid attribute. So if we look out towards the task creation, that they actually discuss the Unix problem, then over here these large train, okay, discuss from here. Each time a new process is initiated, the idle processes are supplied to run the new processes of. If the system is loaded, the processor with least amount of work is assigned. So this is the technique which is already been employed in the Unix architecture. So we'll go to the communication, and before it we are going to see one more thing, that is synchronization. We have discussed it. Okay, there are only two topics which is remaining. So over here, if we go towards the synchronization, so synchronization is needed to protect and shared variable by ensuring that the only element which is placed in a memory has to be acknowledged by other elements. So what we need to do, we need to update other cache memories which has the similar content, so that there is no cache contention problem occur. So there are two main synchronization construct in the shared memory system. What is the one is the locks and the barriers. Second is the barriers. In the figure 4.16a, which is actually the next figure, 4.16a. So what we do, if P1 is accessing a memory, we say it's on a waiting state until the P1 releases the memory module. So in its part B, we saw that P1 is working on some processes, some accessing some memory to do some process, but however others are the P1 which is associated with the barrier 3 has to wait. So that's the chapter summary. A shared memory system is made up of multiple processors. You have to study and read about it. There are also some questions over here, which is actually discussing the mutual exclusion, and it's related to the cache coherency problem. I will going to mark some problems, and that you need to submit and fill and submit before next class. Sunday. That's called to be an assignment. Every class when I will conduct from this week, I will give you assignments so you can readily solve it. So I recommend you to solve the question number um, 3, 4, and 6. 3, 4, 6, 7. I'm going to write on it problem 3, 4, 6, and 7 as time to be submitted before class Sunday. Yeah, exactly. Abdul Wase, that's 3, 4, 6, 7. And so by this we are going to end this chapter. We will have another chapter, which is chapter 5. So we will take a short break and then continue after 10 minutes. Abdul Wase, I will share a link on the Blackboard, and every one of you, not in a group, has to submit this assignment with you on the Blackboard.